Thermochemistry is a study of energy changes associated with chemical reactions and physical changes. After watching the following videos, students will be able to understand the interconversion between different forms of energy and how they relate to the law of conservation of energy. You'll be able to differentiate between systems and surroundings, as well as endo and exothermic processes, and you'll be able to perform calculations relating to the internal energy of a system and how it relates to the heat and work associated with that system. Energy, as we understand it, is the capacity to do work or produce heat. The energy in our universe is constant, therefore providing us the law of conservation of energy, which states that energy can be interconverted from one form into another, but cannot be created or destroyed. This interrelationship or interconversion allows us to take things like chemical energy from, let's say, a fuel source and utilize it to convert into some sort of mechanical energy that can therefore be used in a different way. Now, all energy can either be defined as being potential energy or kinetic energy. Potential energy is associated with an object's position or its chemical composition, while kinetic energy is the energy due to the motion of a specific object. Now, kinetic energy is going to be directly proportional to the mass and the velocity of the object that's being observed. So the two ways that energy can be defined in a generic way are either being potential or kinetic. And as we said earlier, the energy of a system, or the energy of our universe, is constant. So the interplay between the potential energy and kinetic energy of our system depends on situational application. Let's go ahead and let's look at the kinetic and potential interplay between this red and blue ball. Okay, so we have this red ball here that has potential energy. It's set up on a pedestal and it's basically has a stored amount of energy. Okay, now as this ball starts to roll down this hill, the potential energy that it possesses is going to be converted into kinetic energy. And as the ball rolls down that hill, the kinetic energy is eventually going to be transferred into this blue ball once the red ball strikes it. As the red ball strikes this blue ball, it transfers that kinetic energy, and that kinetic energy causes the blue ball to move on to this platform here. Okay, and the final resting state that we have of the red and blue ball is seen here in this model. Now, if we look at this model, though, notice that our blue ball is now in an elevated position than it originally was. Okay, it's no longer moving, so but it has now more potential energy than it originally had in its initial position. Okay, conversely speaking, okay, the red ball now has less potential energy than it had originally. So overall, there's been a change and a transfer in the energy of this system. Notice the potential energy that was stored in this red ball has been transferred to the blue ball to give it a new potential energy value as well as a new position in the actual chart. So if we go ahead though and look at the overall energy exchange, I think it's very easy to see that the overall energy possessed by the final position balls is drastically different than what would be expected over here. If a complete energy transfer were to have occurred between these two balls, we would have expected this blue ball to have reached a higher plateau than what we see here. Okay, and the reality of it is that there isn't a direct transfer because the red ball is actually moving along the surface. Okay, so additional energy transfer is occurring between the environment and the balls. The balls themselves are not the only things that are exchanging energy. So there are two typical methods of energy transfer. You either have work or heat. Now, work is force acting over a distance, okay, and that's the interplay that we see between the red and the blue ball. The red ball is doing work on the blue ball to give it its new position. Now, as we said, if that was a one-to-one relationship or a direct relationship, we would expect the blue ball's elevation to be higher, okay? However, there has been some other mode of energy transfer because the potential energy that was possessed in that red ball did not get completely transferred to this blue ball. So, what is the other option? The most likely option is heat, and heat is basically a form of energy that flows between objects due to temperature differences. So what typically happens in a situation like this is that as the ball rolls down the hill, there's going to be heat transferred caused by friction between the surface that the ball is rolling on and the ball itself. So energy, the potential energy that this ball originally possessed, is going to be lost both in the form of work and in heat transfer onto the surface of the hill that it is rolling down. So energy is either going to be converted into work or it's going to be converted into heat. And basically, depending on the system and surrounding setup, which we'll discuss in more detail, that's going to determine the efficiency of this exchange and the applied goals that we intend from the chemical or from the object that we're rolling down the hill. And we'll look at this in more detail. A state function is basically a property that allows us to determine the state of a system regardless of how that state was achieved. So basically, we ignore mechanisms, we ignore routes that were taken, we ignore procedures for state functions, and only look at their current state. And we can compare two different state functions if we know their initial and final states. It doesn't matter the route that they took. Now, we look at these two hikers and we can compare them. If their position is a state function, notice that the routes that they took to get to their position from their initial state are drastically different. However, because this position or the system is a state function, we can ignore the meandering route versus the more direct route that was taken by each of the individual hikers. So in the previous example that we looked at, the energy of the red ball and the blue ball, the overall energy of that system is a state function. It doesn't matter how their exchange of energy occurred. It didn't matter if energy was lost by frictional heating or if it was lost through work, whatever the process was. All that matters is the final state of that situation or that system. Now, what you must understand is that energy in that situation is a state function. We can ignore the route. Heat and work, however, are not state functions. So you would, if you were asked questions about heat or the work of that system, you would need to account for work being done to the system or work being done by the system or even heat being lost or gained by the system. And we'll talk about that here in a second. So we've been using some vocabulary that needs to be more clearly defined. So basically, chemical energy is the potential energy associated with chemicals. So methane or propane or the gas that's in your fuel tank in your vehicle. These are all examples of chemical energy. There's potential energy in the bonds of those molecules. So when we look at CH4 or methane, we know that it has potential energy. It has the ability to create heat or energy in the form of heat. Now, in order to analyze chemical energy and chemical reactions, so things like this, we must be able to identify what we're looking at. And describing what we're focusing on gives us the opportunity to be able to clearly discuss what's actually happening with respect to the chemical energy of that reaction. So let's first look at our definition. So a system is a part of the universe in which we're focusing on. So the system might be the container in which the reaction is occurring. And usually for chemical reactions, it is the container in which the reaction is being held. The surroundings include everything else in the universe, so everything that's surrounding whatever we're focusing on. There's also different system types. There's open systems, and with an open system, heat can be exchanged as well as mass or matter, so things can leave the container. A closed system doesn't allow for the mass exchange to occur. Because it's closed, only heat can be exchanged. And an isolated system is one in which, theoretically, neither heat in the form of energy or mass of the substances inside the container would be able to leave. So The system, remember, is a thing that we're focusing our attention on, and our surroundings is everything else that's not part of the system. And this is going to be important for us to understand heat flow, energy exchange, and things of that sort. So if we're looking at a chemical reaction and we're focusing on the system, the heat exchange that may occur is going to be described in one of two ways. It's either going to be exothermic or endothermic. An exothermic is a reaction that gives off heat or that evolves heat. Now, an exothermic reaction is going to be losing energy in the form of heat. Now, if we're taking our previous slide and we're thinking about the system, okay, a reaction container that has an exothermic reaction, it is going to get warm. It is going to release heat. An endothermic reaction is a reaction that absorbs energy in the form of heat from the surroundings. Okay, so in those situations, in terms of an endothermic reaction, a lot of times heat is going to be being pulled from the surroundings into the system. So why is this important? Why do we need to think about this? Well, all of the interplay that we've just discussed between potential energy, kinetic energy, work, heat, all those are directly related to chemical energy. So instead of looking at the interplay between the position of the red ball and the blue ball, in this situation we're going to look at the relative energies of reactants versus products, as well as the heat either absorbed or evolved by the reaction that we are observing. So let's go ahead and start with the exothermic process. Okay, so in this case we have our reactants, okay, and they are going to products. Now if we look at the energy associated with the exothermic process, notice that the energy scale here, it's increasing from top to bottom. Okay, so what you notice here is that our reactants start out as a higher energy position relative to our products. So what happens is when we convert from reactants to products, we actually are producing something that has lower energy. Okay, and since energy is conserved, that energy that has been basically converted has to go somewhere, right? And in this case, what we're going to see is that that energy is converted into heat, which is given off by the system. So in this situation, what will happen is the container that we have this reaction in will actually get warmer because the reaction process will heat up the surroundings with the heat that it evolves from converting reactants to lower energy products. Okay, and if we go ahead and we look at the endothermic process over here, so what we have here is we have our reactants down here, okay, and notice our reactant here is lower in energy than our products. So in order to go from our lower energy reactants into our higher energy products, energy has to be added to the system. Okay, so what's going to happen is heat will be added. So what happens is that the surroundings will provide that heat energy. So basically, energy will be absorbed from the surroundings, and what we will see is the production of our new products. Okay, and so in this situation, the container that holds the reactants and is going to subsequently be producing products is going to be pulling heat energy from the surroundings. So basically we should be lowering the temperature of our surroundings, and that energy will be used to convert into our higher energy products. And so basically this interplay is what allows us to analyze what's happening in chemical reactions. And so heat transfer and whether or not a reaction is exo or endothermic is going to allow us to monitor that exchange of energy. The internal energy of a system is the sum of all the kinetic and potential energies of all the particles that are in a specific system. So whatever you're focusing in on, that system's internal energy is going to be related to all the particles' kinetic and potential energy features. This delta E that you see here is the change in internal energy of a system. And that can be represented by the equation here, which shows that the change in internal energy of a system is equal to Q plus W. Q is the heat exchange between the system and the surroundings. Remember, the system is what you're focusing on, and the surroundings is basically everything else. W represents the work that is either done to or by the system that you are applying your focus. So, now, the thermodynamic quantities that we're going to be looking at are always going to have two components. They're going to have a number and they're going to have a sign. The number indicates the magnitude of your change, and the sign indicates the direction of change. And we are going to be looking at these values with respect to the system. Other sciences look at it from a different perspective, but in terms of chemistry, and most chemistry texts are going to look at it with the perspective of the system being the thing you're focusing on. So remember that our change in E is dictated by the sum of the value of Q and the value of W. And Q represents heat and W represents work. So when work is done by the system, so when the system that you're focusing on does work onto the surroundings, your W value will be less than 0. So then it'll be negative. If work is done to the system, so if a piston is pressed down or something of that sort is done to the system, your W value for that specific system will be positive. In that same vein or that same thought process, if a system loses heat, your Q value or your heat value is going to be negative. If the system gains heat, the Q value will be positive. So these types of numerical values will be plugged into the equation here, and that will dictate the overall change of delta E. So depending on what happens with the heat and the work, you may have a system that's losing energy or a system that's gaining energy based on the consideration of both Q and W. Additionally, I want to point out that Q being negative is going to correspond to the system losing heat. We know from our previous discussion that that refers to an exothermic process. Now, heat being gained by the system, or Q being positive, again, corresponds to an endothermic process. So, regardless of what the overall delta E of the system is, we can still have a process that is losing or gaining heat with respect to the system. This problem, they want us to calculate the internal energy of a system undergoing an endothermic process, which corresponds to a 15.6 kilojoule heat exchange, and where 1.4 kilojoules of work are done on the system. Okay, so in this context, we're going to be using this equation. Okay, because we're looking at the internal energy of this specific system. Okay, so we need to look at what's happening to our Q and W, okay, with respect to the system. So Q in this case is going to be a positive 15.6 kilojoules because the system is absorbing heat because it's an endothermic process. And our work value is also going to be positive because the work is being done to the system. So we're going to then take these values and plug them into our equation. So 15.6 kilojoules plus 1.4 kilojoules is going to give us a delta E that is equal to 17.0 kilojoules. Okay, so that's the internal energy of the system. Okay, so whenever you're doing these problems, you want to write out your equation, you want to write out your variables, and then based on the information that they've given you, you're going to be able to figure out the relative signs of your Q and W. Okay, and in this case, remember that because work and heat were added to the system, both our W value and our Q value have a positive sign. So in the previous problem, we looked at the internal energy of a system, and we were given work and we were given our heat value, and basically we just plugged in our calculation. Now, we may need to calculate the work associated with a specific system. And in this case, what we're doing is we are looking at the expansion of a gas in this setup here. And in order to allow us to look at this system and calculate its work, we are going to be utilizing this equation. Work is going to be equal to the negative pressure value, so that's representing the external pressure applied to the system, times the change in volume of the gas. So that's what we're going to see here. Now, we've talked about the fact that when work is positive, there is work being done to the system. Okay, and when work is negative in value, okay, or in sign, work is being done by the system. Okay, so with that in mind, we're going to go ahead and look at this equation here and analyze how the expansion or compression of the gas corresponds to the signs we see for W. Okay, so if my delta V were to be positive, that means that the volume of my gas has increased. So what would happen there is that the piston is going to be pushed up, and basically the gas here is going to be acting against the surrounding pressure. Okay, so I'm going to have a positive value to plug into my delta V, and when I multiply that by that external pressure value, that constant pressure value, and the negative sign, that's going to give me an overall negative W value. A negative W value corresponds to work being done by the system, which makes sense because this gas has pressed against the piston and pushed back against the surroundings. Now, of course, the opposite would be true if the volume of the gas were to decrease. That means that the surroundings are doing work on the gas. We'd get a negative delta V value. When we plugged in our numerical values or into our equation, we'd get a positive W value. A positive W value would mean that work was done to the system. Okay, so let's go ahead and let's calculate our work value associated with this specific problem. Okay, so the first thing we're going to calculate is our delta V. Okay, so in order to calculate our delta V, we're going to take our volume final and subtract it from our volume initial. Okay, and so we went from 46 liters, which is our initial value, to 64 liters. Okay, and so we plug those in, and that's going to give us 18 liters in terms of our change in volume. Now we're going to go ahead and plug these values into our work equation. Okay, so we have plugged in our external pressure of 15 atm. We've plugged in our delta V, and of course we have our negative sign from the equation, and this is going to give us a value of negative 270 liters times atm. Okay, so this is our work value. Notice it's negative, so what that is saying is that the system is doing work to the surroundings, and so another thing I want to point out here, guys, is that obviously the liters times ATM is sort of a unique unit. It's not very intuitive for most of us. So what I want you to understand is liters times ATM. 1 liter ATM is related to this many joules. Okay, and this conversion factor here, you guys should memorize it and be able to utilize it because it will come up on quizzes and tests. You will utilize this conversion factor in order to convert into joules. So in this problem, what they've done is they've indicated that a balloon is expanding in volume by the addition of a certain quantity of heat. Now, we're assuming that the balloon is expanding against a constant pressure, and they want us to calculate the delta E for the process that we are looking at. So we need to know our Q and our W. Okay, so we've been provided Q. Q is equal to 1.3 times 10 to the 8th joules. Notice I'm leaving the sign as positive. Why? Because Q has been added to the system because we are heating the system. And so the Q value needs to be positive. And we now need to calculate W. Now W is going to need to be calculated using our pressure volume calculation. So we need to calculate our delta V in order to calculate W. So we're going to go ahead and calculate delta V. So we take our final volume minus our initial volume, and we get 5.00 times 10 to the 5th liters. Okay, and now we need to calculate our work by plugging that into our work equation. So our negative 1.0 atm times our volume. Okay, and that is going to give us negative 5 times 10 to the 5th liters times atm. And this is our work value. So before we calculate delta E, let's go ahead and analyze how our Q value and our work value correspond to what's happening within our system. So remember, our system is the balloon, and the balloon is being heated. So we have added heat to the system. Okay, so we have a positive Q because the system is absorbing heat. And as this balloon expands, what ends up happening is that work is being done to the surroundings. So we end up with a negative sign for our W because the system is expanding to do work to the surroundings. So we have an endothermic process that is doing work to the surroundings. All right, so we're going to go ahead now and calculate the change in internal energy of this specific system. Okay, so we have our delta E is equal to Q plus W. Okay, now, normally we would just take our Q and our W and plug them in and do the math. However, what I want you to notice is that the units do not match. Okay, so we need to convert into our joules in order to make the units match and subsequently be able to be added together. So we're going to go ahead and we're going to convert our work value into joules. And we end up with negative 5.1 times 10 to the 7th joules. Okay, now we can plug our work and our Q value into our delta E equation. So we go ahead and do that, and that is going to give us a delta E value equal to 8.0 times 10 to the 7th joules. And that is going to be the change in our internal energy of the system.